Good morning, everybody. Thank you for the lovely introduction. I am Malcolm and I work at Nitro. And today I'm going to talk to you guys about something I'm passionate about, which is marrying the ideas of functional programming with ideas of machine learning. So first, I always like to start off with giving a really clear sort of indication of what I want to be talking about today and what I want to communicate. And I have a strongly held belief that I want to communicate today, and that is using functional programming makes it easier to correctly implement machine learning algorithms. And I really want to emphasize this correctly implement idea, because it's very easy to write programs that are fast and get you the wrong answer. They're called system.exit. And it's very hard to implement difficult algorithms. And a lot of machine learning algorithms are mathematically complicated. They have a lot of subtleties. And you can spend lots of time trying to implement an algorithm to be incredibly efficient, especially if it's a machine learning algorithm. Let's say it's a backprop algorithm for training a deep, like a convolutional neural network. You can spend a lot of time making it efficient, and it's incredibly hard to make sure that it's absolutely correct and get you the right answer. A lot of times, especially if you're moving fast, it's really important to make sure what you have is a program that works. And the belief I have is that functional programming makes it easier to make it correct than, say, using another paradigm like imperative programming. So who am I? So I'm a computer science and machine learning practitioner. As was introduced earlier, I got my bachelor's and master's of science and computer science at Carnegie Mellon University. I did research there while I was an undergrad and grad student. I'm currently now a research engineer at Nitro, where they pay me to use Scala and work on natural language processing, machine learning problems, as well as a dash of computer vision. It's pretty great, I get paid to do it. And I'm a big functional programming addict. I haven't gone to FP Anonymous yet, but they tell me it's okay. And I really like being outside. A little bit about me, kind of a gym rat. I sort of like I'm not a gym mouse, so it's too big to qualify for that title. It's a little bit about me. So as an outline, just to give you guys sort of an idea of where I'm going here today, I'm going to talk sort of a little bit more of a motivation around why should you care about correctly implementing. A sort of primer just to get up to speed with some ideas in functional programming as well as machine learning. Some useful for machine learning ideas in functional programming. A couple of classic machine learning problems, as well as so often code that actually implements these ideas. So first some acronyms, in case it wasn't always clear. CS is for computer science, machine learning is ML, NLP is natural language processing, CV is computer vision, and FP is functional programming. And also, before anybody asks about slides, yes, they will be on the interwebs. Actually, I finalized them and I posted them on my Twitter already, so you can actually access them. They'll also be on the Data by the Bay site. And if you follow me on Malk Greaves, my Twitter handle, there's already a link up there where you can download a PDF version of them. So moving on to why should you care about correctly implementing. So here's an assertion. Correctness is the most important aspect of any program. Now my intuition for this assertion is that if the program produces the wrong value, it has no purpose. For example, so let's go over some ideas, two ideas here, what's most important in code. Is it speed is the most important aspect? Sometimes it's make or break. If you have a real-time application, for example, and you don't do, let's say, a stock trade within 50 milliseconds, or you don't make that purchase order in the ad in 50 milliseconds, it's over. You don't have the ability to make it at 51 milliseconds, you're done. So there are some cases where speed, you can get the correct answer, but if it's too late, it doesn't matter at all. But we don't always have a strict deadline. Most of the times in the applications we have to write, it's okay if we're a couple milliseconds late, or maybe it's okay if we're even half a second late. And this is this little joke I had before, right? Is there any program that's faster than startup and exit, right? But do you ever really want something that's this fast, right? If somebody just said, make the fastest program in the world, you should say, great, I can do that. One line, the program ends is the very first thing it does. And that would be, a fast program that you could apply to anything that would always get you the wrong answer. So intuitively, it would be completely useless. And so there's this point, right, that being fast and incorrect is still being incorrect. And so speed is something that's always important in the applications context. If you have a responsive user interface for humans, speed is an important factor. If you have microsecond stock transactions, speed is a very important factor. Or if you're handling lots of requests, then you have to make sure you have high throughput, you don't spend too much time in each request. But in general, speed is important for a particular application context, and fast programs are preferred to slow ones, but I assert that speed is not king. So another idea is readability and maintainability. These are talked about a lot in any kind of software application. Everybody knows, you shouldn't have unreadable code. You should try to write code so that as if the next person reading it or maintaining it knows where you live and is also, a murdering psychopath. All the usual mantra on that. A big reason of that is because a lot of times programs are written not for machines to understand, but for people to understand. So if a person cannot understand the program's behavior, then it's automatically less valuable than a program that could be understood, as you can't gain insight and understanding. And here's a great example. If there's this generalized linear models package in R, it's used a lot. Very fast, great code for making different kinds of linear models. I actually once looked at the Fortran source code because I had a problem with it, and it's about 6,000 lines of Fortran. I don't read Fortran. It's really hard to understand, and I gave up after about half a day of being like, well, I'm clearly not going to solve this problem. I got to find a workaround. But that's an example of I thought I could get some information from this great library. Turned out not to be the case because the code was completely unmaintainable. And as the code wasn't readable and understandable, it was less usable. There's no way for me to extend that code, or just in general, the idea of extending code you don't understand is very difficult. And fixes, of course, are a nightmare. I mean, probably everybody in this room has either been there, or if not, will be in the situation where you have to go fix something you don't understand. And that's very fun. But the reality is, though, we all know this, that there's lots of software in the real world that really nobody understands, and it still works. And it still can be useful. That GLM net package in R is still incredibly useful. People use it a lot. People don't really understand how it works on the internal level. There's only maybe a handful of people in the world that do, but it doesn't mean it's not totally useless. So readability and maintainability is very important as a general rule, but it doesn't make or break a program. So this is, again, going back all the way to this assertion I have that correctness is king. So hopefully I've convinced everybody as why it's important to care about correctly implementing. And so now I want to talk about just some functional programming ideas and machine learning ideas to make sure everybody has a nice background as we go along. So in a nutshell, here's how I characterize functional programming. Everything in functional programs is an expression. Every expression evaluates to a particular value. So there's no delineation between a statement that has some side effect and something that has that value. Every statement always is an expression that you can evaluate to something. And this is a slightly controversial point, but I really feel strongly that functional programming is highly guided by having, at least practical functional programming, is guided by having a strong type system. So that doesn't necessarily mean statically compiled. So like Python's a great example of a language with a strong type system that's dynamically evaluated. You can't do an operation in Python between two types that don't make sense. It'll stop you from evaluating that at runtime. Contrast to a language like JavaScript, which is weakly typed and also dynamically evaluated. If you're trying to add, everybody's seen that there's a great video called WAT with JavaScript. It's got like a duck in it. Some dude's nodding in the front. He knows. It's hilarious. It's great. The presenter in that video shows you can add an empty object to an array in JavaScript, and you get something that's not a number, and that's technically correct, right? And you can flip it around, and you don't get something totally different. So that's an example of you're adding stuff that the types don't make sense, and you shouldn't be able to do that operation, but JavaScript's a language that's weakly typed, so it just attempts to try to interpret that. But not every programming language, there's some untyped Lambda calculus that's not typed, but it's still functional programming, but that's something people could disagree with me on, but I think that's my strong typing point. I'm sticking to it. Another important aspect of functional programming is that, this is not controversial, that functions are values. So there's no difference in how you use, say, an integer versus a function that goes from one integer to another integer. They have different applications, but you can still reason with them in the same abstract sense that you would a single value. Because in functional programming, they are essentially a value. So you can pass them around, you can reason with them like any other variable. There's this other concept called referential transparency, which really what it means is that if something evaluates to x, it's equivalent to x. So if you have a definition of something that's more complicated and it evaluates to 5, that's the same thing as a variable with the value 5, right? How you computed them is different, but essentially they are the exact same thing. There's just different ways to get there. So this is important because if you ever have a function definition and an input, and you evaluate it to an output, that's always going to be the exact same output. In a purely functional programming sense, there's no difference between a function applied to an input and the resulting output. And I just wanted to get this out there. If anybody in the audience is wondering, what do I mean with programming with functions? I mean something sort of more like this. So in an example in Scala, if you want to make a function add 1 to its input, not very interesting, but simple, you would simply declare a function, add 1, it goes from int to int, and then you'd use it. You apply 10 to the function, and you get the value 11. If you're doing the same thing in Python, you would make a variable called add1, you'd make an anonymous function in the same sense, that adds 1 to its input, and then you can apply 10 to it and get 11 as well. What I mean, don't do this better, make functions, just use them directly, instead of sort of a more object-oriented approach, where I'm going to use Java as an example, where you could make, you'd make a singleton class, it has a method add1, it takes that number and add ones, it returns it, and when you want to use it, you have to make a new instance of that object, and then call the method on it as well. And I argued, right, you could make the argument, well, this object's method is a function, and Scala kind of does it behind the scenes of how it implements it, but really from a kind of language use case perspective and how you use a language, these are slightly different concepts and slightly different, right? In the object-oriented sense, you're making objects and then calling methods on them. In the function case, there's really no distinction. You just have functions and you can apply them. So it's a lot simpler machinery, a lot easier to reason with in your own head. So moving on to just sort of machine learning in a nutshell, some of the ideas I just want to get out there before I start talking more in depth, is that everything in machine learning needs data. So the effectiveness of any machine learning algorithm is completely directly dependent on your data quality. There's a lot of it that happens with the algorithm you're using, but if you have garbage data in, you're going to get garbage data out, no matter what. So the reason why that everything in machine learning needs data is that everything that's pretty interesting in machine learning uses statistics. And if you have any machine learning algorithm, when it ingests data, the output of that algorithm is always a model. And these models view the world through features, and the features are things like its attributes or properties, or if you look at like a matrix perspective, instances might be rows, and then columns might be features. So it's kind of like a database record, right, where columns are features. And this is just sort of a very kind of broad 30,000-foot view of just machine learning. Now machine learning has one really big aspect, or class of machine learning algorithms that are called supervised learning algorithms. And I kind of like to coin this term as the AI of machine learning. Why? Because supervised learning really has the most interesting applications of machine learning. For example, driving a car, translating from one language to another language, recognizing objects in pictures, searching for images in text, all these really interesting things that we like to think of as intelligent or smart behaving programs really, at the end of the day, will use supervised machine learning. And in the supervised machine learning sense, the objective is that first you assume that there's some function that exists in the universe that goes from your input to your output. So if it's driving a car, it might go from the input of, here's a picture of the road, to the output is, what angle should you turn the steering wheel? How much should you apply the gas? How much should you apply the brake? And you assume that that function exists. And you say, well, the function must exist because I can drive a car and you can drive a car. And so, we all sort of have a sense of how we can drive a vehicle. And there must be some universal function that tells us how to compute this. And so now, given that we assume that that function exists, what we're trying to do is, with a list of input and output pairs, find a function that approximates this special function f, the one true function for driving, right? Or the one true function that you assume exists for your specific task at hand. And this, by the way, this is just sort of a theoretical academic setup. It's important in sort of your line of rigorous thinking. It's not something you say, okay, where's this function? But it's just how to set up the problem in your head so you can think about it. There's other types of supervised learning. In the probably broadest sense that people know, there's classification. So you have an input and your output is one element from a discrete category. So it might be binary classification where the categories are 2, yes and no. It might be multi-class classification. It might be like a tag on an image. Is this a picture of a room? Is this a picture of a house? Is this a picture of a cat? Those would all be classification. An example I have here, right? Everybody probably uses Gmail, or at least knows what it's all about, knows about the priority inboxes. And that's a great example of classification. When you get an email message, how should you categorize it? Should it be spam? Should it be priority messages? Should it be family? And what's nice about classification is that it lets you have a model that's able to make a decision, which is very useful. Another type of supervised learning I'm not really going to talk a lot about in this talk, but I want to point out is that there's a thing called regression. So you guys probably heard of linear regression. Similar setup, but the idea is that you're not predicting a discrete category, you're predicting a continuous value. So if you have an apartment listing, could you predict what the estimated rental price is? That's not, 10, 20, 30, that's a real value number that could go anywhere, technically an infinite number of possibilities. So classic algorithm is linear regression, right? And another type of supervised learning is called structure prediction. So this is similar to classification, except the output is significantly more complex. So for example, if you had a sentence, and you say, given this sentence, what's the syntactic dependency parse? What's basically the tree structure describing the grammatical relations between every single word in the sentence to every other word? There's a lot of different kinds of structures there to predict. So, and because it's a tree, there's lots of different trees. It's significantly harder than just trying to predict, what sort of label the outcome is. And it's very, very interesting. Not going to talk about it a lot in here. I just want to kind of give everybody a primer on that. There's another big kind of machine learning called unsupervised learning. So in unsupervised learning, it's pattern recognition through and throughout. It's not doing anything like supervised learning. It's not, you don't have a training set of labels and unlabeled stuff. And the output is not a model. The output is a set of patterns that are expressed in the data. So for example, if you're doing something like k-means clustering, the output of that unsupervised learning algorithm isn't, here's a model to do classification. It's, here are the centers of 20 clusters I found, or 10 clusters, or how many clusters you asked me to find. By themselves, the output of unsupervised learning doesn't do classification, regression, or structure prediction. As a human being, it's your responsibility to interpret those patterns output and then figure out a way to make them useful for your problem. So if it doesn't give you a nice thing to use at the end of the day, why would you ever use unsupervised learning? Well, the reality of the world is that the overwhelming majority of data is not labeled. You don't have nice pairs of input and output, you just have the input. So in this sense, if you don't have pairs of input and output, you can't do supervised learning, full stop. So that's where unsupervised learning would be helpful. Additionally, unsupervised learning is helpful for trying to understand the data. So if you're just a human being, maybe it's your first approach at a data set, it's your first day on a new job, you just want to get a sense of the data, digging into some, applying some unsupervised learning algorithms might be useful for you to get intuition of what's actually there. It's also very useful for search. A lot of problems, searching problems can be sort of formulated as an unsupervised learning problem. And additionally, the last kind of point is, once you find these patterns, if you as a human do some additional manual work on top of this, oftentimes you can engineer an okay solution, possibly good, but some sort of solution for some sorts of classification problems. For example, if you had a program that output clusters, and you could figure out how to get one of those, your inputs to match up to a cluster, you might then look at those clusters as a human and manually assign semantics to them. You might say, well, this cluster, I'm declaring this cluster represents a certain category. So that's an example. You can kind of sort of bootstrap a classification problem on top of an unsupervised problem, but it requires human input at some stage in order to go from unsupervised to supervised. So now moving on here, I'm going to try to go a little more quickly because I think you guys are interested in seeing some code or some useful for machine learning ideas on functional programming. So first is just this concept of just using the type system. So a large part of practical functional programming is to use types to guide the program's logic. So it eliminates lots, but not every single logical error. So for example, the biggest part of having a statically evaluated type system or a strong type system is that you can't make a program that applies a function, for example, to go from one type A to another type B to a value of type Z. That just doesn't work. That doesn't make any sense. That's like trying to add an integer to a string. It makes no sense. What does it mean to add 5 to the word the? In practice, if you come from a Java world, this means you don't have to have any more as instance of or casting in order to circumvent the compiler and say, no, trust me, this type is actually this type. Or in Python, right, this is my little jab at the Python community. They're nice people though. Is that, a lot of time in Python code, you'll get an input and the very first thing it does, it checks the type of the input. And it says, if it's this type, run this thing. If it's this type, run this thing. If it's not any of those types, then throw an exception. That's basically trying to do static, like bolting on static type evaluation into a dynamic language. And And so the big part of why would you use a type system, why would you have a statically typed system, is it lets you eliminate a whole class of bugs from a program, namely type errors. You won't run a program that has a type error in it if you statically evaluate them. And that's very nice, especially if you're developing fast. You can save a lot of time, wasting time kind of doing some more kind of boilerplate-y type checking stuff. So probably a lot of people here have used Scala. Just show of hands real quick. Yeah, so you guys all know the hello world of Scala collections, right? You got some data, you can map over it, you can filter over it, you can flat map. And each time you do this, right, it evaluates a whole new value of that sequence. So Scala crowd in here, so you guys know a lot of these ideas probably about using kind of higher kinded types. So for example, if you have something that could evaluate nothing, then you want to use this type an option to encompass that idea that this might not be whatever you want. If something's going to take some time, you don't know if it's going to come back immediately. You'd use a future to indicate that whole concept. If something's going to fail, you might use the built-in Scala try type, or you might use the Scala Z disjunction type, which is very similar. If anybody's not familiar with Scala Z, the disjunction type, that little character, I agree, the little V is a little weird. But essentially, you can always say this. You have try of T, it's exactly equivalent, more or less, to a disjunction of a throwable as the error condition, and a T as the correct no error condition. And these are an example of higher kinded types. So higher kinded type is a type that has a hole in it. So it's an incomplete type. Once you fill in the hole with another type, you get a whole complete type. So for example, an option is a higher kinded type because without that specific inner type, it's not complete yet. And I like to look at higher kinded types as they have a value, some value T, within a context. And you'd indicate this as K of T. So moving on to this other idea called type classes, just kind of quick, I want to make sure, just a brief intro here. So start off with a tale of two types, X and Y. All you know that X is able to do actions A, B, and C. Y is able to do actions A, B, and C. And you're posed with the question, are X and Y the same type? If you use subtyping, you have to ask the questions, well, are they subtypes of one another? Are they children of the same parent type? And are you trying to see if they're the same by looking if they're the same parent type? With type classes, the way you answer this question, are they the same, is you say, is there evidence that says X behaves as Y, or vice versa? And so type classes, the idea is that you put a constraint on a certain type. You say, with me, as the type class, I can show you how any instance of type T adheres to this interface. And why would this idea be useful for machine learning? A lot of times you want to do stuff with numerical vectors. You don't really care if it's a dense vector of doubles or if it's a sparse vector of integers. You just sort of want to be able to encode the idea, hey, I've got something that can do vector operations. Let me do vector operations on them. Or arithmetic operations. I don't really care if it's a double or an integer. I just want to know if I can add them, divide them, or subtract them from one another. Or for kind of other algebra ideas, for example, from the Breeze library, Spire library, you want to just know, hey, I have something that you can combine together. Okay, that's great. Now I know I can do a reduce on them. And also an idea for data, right? A lot of times Scala collections, it's very nice. The higher order functions, map, flat map, filter, and such are very useful. And you just want to be able to say, I don't really care what kind of piece of data this is. I just want to know if I can map over it. And there's this idea that I kind of sort of came across and like to coin it in my head as this type class for data of all sizes. And so this is a great kind of what I'm talking about, right? When we have data, we sort of just care about these higher order functions to transform the data so we can operate on it. We don't really care if it's a Scala sequence or if it's a wrapped sequence or an array or if it's a traversable or iterator. Like, we really just care if we can do these things on them. Or if it's a Spark RDD, we don't really care. We just want to be able to describe our algorithm in terms of these operations. So in the same sense as before, instead of saying, I don't really care what the type is, I just want to know that I can do these operations on this type. We want to be able to say, all I want to know is that I can do a map, flat map filter on some type D. And so there's this thing I created called the data type class. As a quick short definition, this is actually not the whole of it, but this is like what it would look like for map and reduce. You would define something saying, okay, well, I have this trait, data. The specific type of the collection is D, has a hole in it, so you know it's not totally complete. and you're saying, okay, well, I can map over it if you give me an instance of it, of type A, a function from A to B, and I'll tell you how to turn it into a collection of type B. Similar thing for reduce. If you give me an example of it for type B and a function to combine two values, I'll tell you how to combine them. And just as a quick note here, this little type class annotation comes from the Silacrum project, which is really great. It's a macro that allows you to get access to sort of make this syntax a little nicer. So instead of having to say, map of the collection, it essentially allows you to say the collection dot map, which is a more sort of functional, more approachable object-oriented syntax. And you can get access to that, for example, in this case by saying import data.ops._, because the macro makes an object that has some implicits in it under this thing called ops, and if you import that, you'll be able to get this syntax. Just a nice thing if you guys are using this on your own. So here's an example of kind of implementing them for two different things. Here's for implementing this simple data type class for a sequence. It's pretty boilerplatey. You just sort of kind of plug and chug. Similar thing for an RDD. If you have an RDD of type A and a function from A to B, you simply call map on it. And these look almost the exact same implementation-wise. And that's kind of the point, is that these are examples of two kinds of totally different collections that have the same, almost the same behavior. So our implementations for them are basically the same, but it allows us, something we'll see later, that we won't have to really worry about trying to say, okay, well, I got to re-implement my whole algorithm for a Spark IDD. I just did it for a Scala collection. Like, well, why do I have to do this? It doesn't really make a lot of sense. But that is sort of the big way of using these type class ideas. So just an example of using a type class idea in Scala, or type class in Scala. Let's say we're going to use the data type class. Let's say we're going to make a function to sum over some collection of doubles. So really simple, right? You can take a reduce first and just add every single number together, and you'll get the whole sum out. And this is great because this you could use it on, if you go online, you can see there's implementation for RDD, there's implementations for different Scala collections. You could use this code right now and have a generic summing function for doubles. But why stop there? Wouldn't it be nice if you could have just a generic summing function for anything that's a number type? So there's a built-in type class in Scala called numeric, and you could say, well, now I have a data collection of numbers. I don't know what kind of number they are, but there's some specific number type. And now I could do the same thing. I say, well, data.reduce, and I have two values. How do I reduce them together? Well, I would get the evidence saying that n is a numeric type, and that numeric type has a function called plus, and that adds two instances of n together to get another instance of n where they're summed. So in this case, right, now we have a whole algorithm that is very generic. It can operate on any kind of data collection, as long as you have reduce and map, and any kind of number type, and you can add it. This would work for an RDD of ints or a sequence of doubles. And this is kind of the level of abstraction we want. We don't really, especially when we're trying to implement machine learning algorithms correctly, we really don't want to have to be dealing with, we want to, as much as we can, not deal with the low-level concepts, such as what's the specific number type, what's the specific collection type. We sort of want to make sure our algorithm's correct, and then sort of use as many tools as we can to help us extend that and apply that correct algorithm to different problems. And a quick note on numeric. So numeric is this type class in Scala has plus times minus. There's another one called fractional. So it's the same thing, but it also has a divide operation. So if you were specifically working with doubles and floats and you wanted to be able to divide, it'd be a little bit better to use fractional. So as a quick thing here, this type class of vector operations essentially is, there's another one I use in some of the code here, and the big idea is that you want to be able to say, I've got two numerical vectors, and I want to be able to add them together or multiply them or do the dot product. So in the code, if you see a thing called math vector ops, that's a type class for supporting those sorts of operations or anything that behaves like a numerical vector. Alrighty, so I've got 10 minutes left as I've been informed. So I want to talk about some of these classic machine learning problems, sort of more older school problems, not deep learning, but I think they're really great for illustrating these points. So I'm going to talk about 3 problems. 2 of them are unsupervised, the searching and clustering, and the classification is the supervised problem. So there's 3 different learning problems: clustering, classification, and search. And we're going to do clustering with k-means, and I'm going to show that algorithm and then some code for it, searching with nearest neighbors, as well as classification with k-nearest neighbors. And then I'm going to start off with a little blurb about vectors, because I've been kind of talking about them without really giving them at least a slide on their own. So if you hear me interchange the word vector for input or an item, what I mean is, by vector, I mean a numerical vector from linear algebra. I don't mean like a Scala vector collection where it's like an array or an appendable array. I mean something that, lives in a vector space, you can do dot products on, matrices, that kind of sort of jazz. And in machine learning, basically you can think of every single algorithm as input always takes a feature vector. And by feature vector, I mean it's a special kind of numerical vector. There's always this sort of context of a map around, which says, if you give me a feature, I'll tell you how to go to a numerical index from 0 to n minus 1 for n features. So that if you give me a vector, we can use an integer index. So you can go in this vector, integer or index 500 or 525, right? What's the feature for that? Okay, I can go to my map and find that again, and I can also then find the feature value for that. And that's just sort of the general approach for every single machine learning algorithm. So if you're ever in a talk and somebody talking about items and inputs and then switches to vectors, don't worry, you can think of them as the same thing, at least conceptually. So now I want to talk about this clustering with k-means problem here. So k-means is an unsupervised algorithm. Its input is just a list of vectors, no labels, and a number of desired clusters to be discovered. And the output is the k vectors, each one is a center for one of these clusters. And the immediate question is, great, cool, it clusters, but what can I use this for? So you can use clustering with k-means as the canonical ways you can, once you find these clusters, you can then assign any old vector to a cluster. You could also do something like soft k-means, where you say, well, this vector isn't necessarily assigned to a cluster, it has membership, a partial membership between clusters. And why would you want to do this, right? Well, the utility is, if you, as a human being, observe what these clusters are, look at the examples closest to the clusters, then you can, and you go and you find the original inputs for these close vectors. You can then manually understand what these clusters are representing if you put some thought into it, and you could impose meaning on these clusters by looking at the representative items and saying, this cluster means this. So you might have, for example, let's say you're doing document categorization. You just have a bunch of documents, you turn them into vectors, you cluster them, and you look at the, for each cluster, the 10 closest documents that are assigned to the cluster, and you look at them and say, well, these documents they're kind of about legal stuff. So I'm going to just say, this is now my cluster representing legal stuff. And these documents over here in this cluster look like they're kind of more about tech company recruiting posters, right? Or tech company recruiting emails or something. So that's what I mean by sort of imposing meaning on these representative items. So switching over to nearest neighbors search. So nearest neighbors is also unsupervised. Its input is also just a list of vectors. Its output is a program that has the ability to list items that are similar to another one. So if you have, so it's a general purpose search algorithm. There's no training or learning. Pretty easy to parallelize and implement, and it's easy to experiment with different features, different distance measures. And you could use it to answer the question, if I have some X, what are the ones that are similar? What are the 5 closest or 5 most similar things to this input? You can use it for documents, dating profiles, literally anything you can be turned into a feature vector, you can use nearest neighbor search on. There's sort of an adaptation to nearest neighbor search called k-nearest neighbors for classification. It's really similar. The idea is to make it work well with label data in order to get something that you can use at the end of the day for doing classification, which is a supervised problem. So its input is a list of items with labels, and your output is a classifier that goes from item to label. What can you use classifiers for? So they're for decision making primarily, so-called smart programs. Specifically k-nearest neighbors, why would you use this than something else? Its main is it really doesn't have any training time, so it's great for if you just accumulate data, you can just build up a big corpus of data. You can parallelize the classification parts, same logic as nearest neighbor searching, and its key is it's really easy to implement and it's easy to test on completely new problems. So it's not something you might want to use in production, it's something you might want to use right at the beginning of sort of an exploration. Okay, so now I have 5 minutes left for code, which is great. So these slides are online, so I'm just going to go through all these links here, or just show them. So there's some links for the type class, the data type class I was talking about, that type class for math vector operations, an algorithm for k-means clustering, one for nearest neighbor search, one for k-nearest neighbors, and also link to this classic old school 20 newsgroups data set. So first on K means clustering. How does this algorithm work? The algorithm is you initialize the centers randomly. You just choose weights for the, you just randomly initialize the vectors using like Gaussian weights or uniformly at random. And you say while these centers are not converged, for each vector in your data set, you assign that vector to the clusters nearest. And then after you've done all the assignments, you recomplete the cluster centers by averaging all the vectors that are assigned to it. So you move those centers to where they're now the average of the things assigned to it, and you repeat. And converged here means that you usually define this as saying, well, they've converged if that the centers haven't moved by more than a small margin between iterations. So if they start slowing down and moving from one center from one iteration to another one, once that's sort of slowed down, then you say that's converged. And that's a parameter you can kind of play with. In nearest neighbor search, the algorithm is for each new item, convert it to a vector. And then when you're given a new item, you convert it to a vector as well. You calculate the distance between that item and all the other vectors. And then you sort that. You can think of it as you sort the resulting list. You take the shortest distance at the top, and then you return the closest k. K is a small number like 5, 10, 20, 100 vectors, and you return those vectors for the new item. And that's your end of the day output. K nearest neighbors is really similar. For each item, convert to a vector, given a new item, convert to a vector, calculate distance, sort resulting list, blah, blah, blah. But then the difference is, once you get those k vectors, they also have little labels assigned to them. So then you say, okay, out of those closest k vectors, what's the most frequent label that appears? That's the majority label. Return that as the label you're going to classify the item as. So right, everything up to the very last point is the same thing as nearest neighbors, and only the new part is that the sort of logic to deal with the labels. So with my last 2 minutes here, I'm going to frantically try to show you something sort of cool. So I do have an IntelliJ window open, which is, nobody can see this anymore. But so this is, oops. Okay. So this is a little program I have that I wrote sort of quickly. What it's really doing is it's sort of reading these trained news groups data file. You can think of each file belongs to a certain news group, like computer politics or science or different kinds of groups, and they're message board. So it's sort of old school form message boards, people posting back and forth. And this first part of the program just loads data up, and then what I do is I say, okay, after I load up all the data, I'm going to make a new KNN classifier, and I say it's going to work on the thing it's going to classify as a document, where saying a document is just a string, the label's a string, the number type's a float, and the vector type is a sparse vector. And a little thing to turn, this turns strings, documents into sparse vectors. And I set up the train and test things right here, and then I do is like, great, I'm going to go build my KNN model on this data. I'm going to take the top 25, and then I'm going to go classify and see how this rolls. So we're going to go and run this live, because that's always fun, especially in the demo on stage. So, okay. So it's really simple. I have the data already loaded on my computer, so it's going through all the news group stuff, getting all those documents in each one, turning them into vectors, and then it's going to go split them up to just ones that the KNN classifier uses, and then a separate 2,000 documents that it's going to use testing from. And it's now taking random documents, trying to predict. So in this first one, for example, it predicted that the broader category is from science. It actually was the miscellaneous category. It got that wrong. So it's got a terrible 12% accuracy. So KNN, right, it's not always the greatest, the most accurate algorithm, but it's easy to implement and it's easy to kind of get working. And it's very, very, very extendable. It's very adjustable. There's a lot of things I could do to make this better. But I just wanted to kind of show you guys that this stuff does work. If I had a little more time, I'd love to show you some of the code. If you want to talk with me afterwards, I could. Everything's also online. And the slides are up, and you can go through the links on there. I'm out of time, and thank you for being a wonderful audience.